Thank you for joining us. We're the Martian Exploration Team, and today we're excited to share with you our plan for the establishment of a sustainable Martian habitat, which will pioneer the way for revolutionizing exploration, as well as lay the foundation for humanity to one day be able to call the Red Planet home. Let's get started.
Hi, my name is Fiechtner, and I'm from Parker, Colorado.
Hi, my name is Kate Williams, and I'm from Shawnee, Wisconsin.
Hi, my name is Elizabeth Halton, and I'm from Ithaca, New York.
My name is Mila Jones, and I'm from Fort Worth, Texas.
Hi, my name is Samantha Estrada, and I'm from Murrieta, California.
Hey, my name is Srivastava, and I'm from Glastonbury, Connecticut.
Hey, my name is Patino, and I'm from Houston, Texas.
Hi, my name is Jonas Moreno, and I'm from Mill Valley, California.
Our program mentors are Dr. Humboldt Mandell and Adam Nokes. Our product associates are Marshall Morey and William Matthews.
Our presentation will begin with the structures, crew systems, and systems integrations team, then the environmental control and life supports team, followed by the communications and power team. We will conclude with our closing remarks and acknowledgements.
And now for the big question, why Mars? So in a nutshell, we must look to the past to answer this question. Insight, ingenuity, curiosity, perseverance, all words that embody what it means to be human. So the answer is simple. We go to Mars because we are human. We go because we must push the limits of our humanity and build the future that lies ahead for mankind. So I ask you this question, for that endeavor, what better place is there than Mars?
Our group was challenged to create a functioning Martian base that is capable of supporting 14 people for at least 26 months. We have decided that this base will be located at Jezero Crater.
Hello, everyone. I'm Eric, and I'm part of the Structures, Crew Systems, and System Integration team with Kate. Our goal was to incorporate all subsystems to create a cohesive base.
These are some of the requirements our group was tasked to fulfill. Our base will primarily host 7 people, but is capable of accommodating 14 in case of emergency. They will all be kept physically and mentally healthy with the necessary services provided. Our total radiation exposure for the astronauts will be less than 50% of their career limit so that it will be possible for an astronaut to have 2 missions to Mars. Our base will have 3 habitat modules, Dragon, Griffin, and Pegasus. Each habitat is equipped with an airlock and tunneling systems to other habitats with multiple exits in case of emergency. As you can see, the Griffin module has a rover port for direct transfer from pressurized rovers to the habitat, as well as a rover maintenance facility attached to the Pegasus module.
One of the challenges we will face on Mars is exposure to radiation. Radiation can cause many issues to astronauts, including lower cognitive function, increased risk of fatal cancer, and immediate effects such as radiation sickness. In our landing site of Jezero Crater, astronauts will be exposed to 0.43 sieverts for the 26 months on the surface. To put that into perspective, on Earth, we're exposed to only 0.013 sieverts for the same duration. On our base, we have been able to reduce the dosage from 0.43 sieverts to 0.232 sieverts, and that's about 15% of the female 35-year-old career limit for an astronaut. Our modules are designed to protect against the constant shower of radiation from galactic cosmic rays. The first layer of aluminum and Kevlar both serve the purpose of shielding against radiation and protecting against micrometeorites. Our next layer is water. All of the water will be in a closed system within the walls of the modules and will help also shield from radiation. Finally, the innermost layer of aluminum will be used to pressurize the modules and will also serve as the last layer of protection from radiation.
The top floor of the Dragon module will include 7 rooms capable of supporting 14 people. Each one of these rooms will be equipped with a bed, a cot, and a personal workspace. The Griffin module's top floor will include a gym that will accommodate astronauts in microgravity on Mars. It will also have an emergency room, communication center, and storage. The Pegasus module's top floor will mainly be used for the 3D printer space, lab space, and extra storage that is needed. Griffin and Pegasus will also include a window and a bathroom on each top floor.
On the bottom floors of the modules, Dragon will have a kitchen, that includes our greenhouse, a multi-purpose room, a bathroom, and an area for storage and lab space. The Pegasus and Griffin modules will be dedicated to more storage and lab space. Each module also has a ladder in the middle, and that allows for easy movement between the floors. The rover maintenance facility will serve 2 purposes. The primary purpose is to perform repairs on rovers and any other machinery for the base. The secondary purpose will be to further protect from radiation. In addition to galactic cosmic rays, Solar flares are another form of radiation that Mars is subject to. Solar flares are high energy particle events, and when detected, our crew will relocate to the Rover Maintenance facility where they will be better protected with a thicker layer of water in the walls.
18,000 kilograms of food will be required for this mission. This includes an assortment of irradiated food, which allows for more nutrients and a longer shelf life, dehydrated food, which will have a longer shelf life and lower mass, but a limited variety of food options, and thermostabilized food, which has a shorter shelf life, but tastes the most similar to food on Earth. Packaging accounts for 15% of our total food mass. A majority of this food packaging will be able to be repurposed by the 3D printer on board. Additionally, all of the food will be stored in international standard payload racks. We have decided to use the Texas Microgreens automated planter and processor as our initial crop production. It will include a food processing system and a fully automated compost. Even though it will only produce 140 to 300 kcal per day, it is still very important to start a foundation of crop production on our base for future missions, crew morale, and research on how growing plants can differ from planet to planet. In order to be self-sustained on Mars, we would need a large amount of space, mass, and crew time. For the initial mission to Mars, it is unrealistic to say that we will have access to all of these necessary requirements to fulfill this. Thus, this means we have decided to only bring one TMAP.
Now, Elizabeth and Mila of the Environmental Control and Life Support System Group will talk about their contributions to this project.
Hi, I'm Elizabeth. Mila and I are in charge of the Environmental Control and Life Support Systems, or ECLIS. ECLIS is responsible for creating an environment the astronauts can live in. It provides clean air and water for all crew members and systems for the entirety of the mission. The exact figures of these requirements are on the slide in front of you. They're provided for by 5 ECLIS units across the habitat, 3 are turned on, and 2 are backup.
The air management system regulates the atmosphere quality and limits the concentration of contaminants through filtration. The revitalization system recovers 99% condensate, maintaining a composition of 79% nitrogen and 21% oxygen. The oxygen generation system, or OGS, is connected to the water reduction system, where water is electrolyzed to obtain hydrogen and oxygen. Air with CO2 is processed through reduction systems, which processes a byproduct of water. The thermal control system regulates the temperature at about 73 degrees Fahrenheit and maintains a 60% humidity, and it also regulates air circulation. To address the low temperature of negative 117 degrees Fahrenheit, ammonia-based heating pipes and multi-layer insulation will be used. The water recovery system, or WRS, provides safe water for the habitat. The WRS recovers 93% of the water it cycles through. The cycle, which takes about 54 hours to complete, begins with the urine collection system, where urine is pre-treated with chemicals then combined with fresh water. The urine processor assembly produces a distillate, where the water processor assembly, or WPA, separates any gas from wastewater. WPA sends the processed water to a storage tank. All storage tanks are located in the walls of the habitat. Some water will be transferred to the OGS to aid in CO2 reduction before it gets recycled again. The fire detection and prevention system works on reducing the risk for fire propagation by keeping the oxygen concentration below 30% and by facilitating fast reactions in the event of a fire. The trace contaminant control system has the capability to remove carbon monoxide and acid gas. Sensors detect temperature rise, combustion gas, and pressure rise. There will be both CO2 and fine water mist extinguishers. The major constituent analyzer monitors air composition, and the rack power switch allows the crew to turn off the entire rack in the event of a fire. Waste management focuses on recycling and disposing of waste. Solid waste is separated where wet waste continues to the wet waste processing unit, which recovers water. The 3D printer recycles plastic and foam. The remaining solid waste is addressed by the Orbital Syngas Commodity Augmentation Reactor, or OSCAR. This reactor utilizes the idea of trash to gas by converting waste into hydrogen, CO2, methane, and water through heat. Any leftover waste, called slag, is combined with glass to create non-toxic building material. Urine is collected and sent to the water recycling assembly. Plant waste is composted by TMAP. This all supports a zero-waste system. Elizabeth will now elaborate on the storage of the ECLIS systems.
These systems are stored in modified international standard payload racks. These are the racks used on the ISS and other spacecraft that have been modified to fit our exact dimensions. You can see a CAD of these on your right. The extravehicular activity suits, or EVA suits, are what are worn by the astronauts as soon as they leave the habitat to explore Mars. We are implementing the proposed MEMU suit design that is currently being designed for the Mars environment. They are an adaptation of the currently used EMU design for the ISS. We will have 10 suits on the spacecraft, 7 for the main crew, and 3 to provide redundancy. Repairs in the habitat will be covered by a 3D printer. This printer turns plastic and foam waste from packaging into filament that is then used to print out different repair parts. These parts are very useful, but the plastic has a limited amount of times that it can be run through the printer before it loses structural integrity. Here you can see all of the Eclipse racks in the CAD model of the habitat. The Eclipse racks line most of the walls, and the EVA suit racks, which are designed specifically to fit the suits, are by the airlocks where they will be used. Now, onto communication.
Thank you. We're the communications team, and let's get started. Now, communication consists of 2 categories: transplanetary communication and local communication. Optimally, with a communications link between Earth and Mars supporting video, which requires a bandwidth of about 2 to 5 megabits per second, we can also support voice and telemetry data relatively easily. As for local communication, Jay?
Yep, so as for local communication, we're working on creating a versatile network which we can expand on in future missions. We're really focusing on laying down that foundation. And in order to do that, we want a network that is, as you can see on the screen, flexible and expandable, and it would also be very nice to be high speed. But I'll talk more about that in the future. For now, Sam with transplanetary communication.
And now for a deeper dive on Mars to Earth communication. Given that sending information directly from the Martian surface to Earth would be difficult, an alternate approach is needed. The figure that you see here makes use of 2 radio relay links, one from the surface of Mars to an aerostationary satellite orbiting Mars via UHF transmission, which is optimal for this shorter distance, and another link from the satellite to Earth's deep space network via a high-gain antenna, which focuses the radio transmission to optimize signal strength, accuracy, and range over long distances. Now, a satellite for a manned mission must have more expanded capabilities than what has been used in the past, namely the Mars Reconnaissance Orbiter. For this reason, the satellite we will use will have more antennas, thus making it capable of establishing relay links from multiple directions, will support a higher bandwidth through the use of Ka frequency, which is 4 times more efficient than what has been used in the past, and therefore will be capable of supporting video consistently. As for communication during blocked windows, such as when Mars is blocking transmission to Earth, a relay link between the primary aerostationary satellite and a secondary satellite in polar orbit will be established, thus ensuring continuous communications capabilities between Mars and Earth. Jay?
So now for communicating on Mars, or local communications. And just for a little bit of context, to explain more, the main local communications will consist of either communicating from different buildings in the HAB, such as the Greenhouse and Communication Center, or communicating to things like rovers. And the primary method that we chose to carry this out was small sats, as you can see on the screen. By definition, they're specialized miniature satellites. This means they're about 180 kilograms, and they're about the size of a kitchen refrigerator, which in terms of space is extremely small. And the reason they're so interesting is because they're so small. They're so low cost and easy to build that you can easily get a lot of them into Martian orbit, creating a fast network with little to no cost. They act as part of a larger infrastructure in order to give data, as they can act as assets that both give and receive the information. And they also use ultra high frequency, which is optimized for its distance. Again, I cannot stress enough, these things are revolutionary in terms of space communications, and you'll definitely be seeing them more in the future. As for our redundancy strategy, we chose to adopt a system called MarsNet, which takes use of the 2 satellites that Sam mentioned earlier. These also use ultra high frequency due to the local distances, and how they act is by using orbital relay nodes, which, as I can say again, is sending and receiving data to assets. These things, as you can see, are scalable, fault tolerant, redundant, and extensive. The reason why they are all of these things is because they take advantage of impromptu window openings instead of the planned IP style delivery which systems previously used, making it up to twice as fast and more reliable. Now I'm going to hand it on to the power team. Jonas and Rebecca, take it away.
If you lose power on Earth, you tough it out for a few days. If you lose power on Mars, you die. Dr. Mandell. Having enough power is essential to the functionality of the mission and the survival of the crew. So it was Jonas and I's job to investigate how much this mission would require and find out how we would allocate all of it. We concluded that we would need to produce about 46 kilowatts and decided that the best way to do this would be using 3 small nuclear reactors and 2 different types of solar arrays. Here's the power breakdown for the estimated power budget. Now we will introduce how we will go about obtaining it.
20 months before our crew ever touches down, an Earth return vehicle carrying an in situ resource utilization unit, ISRU, and 3 kilopower reactors lands on Mars. Instead of bringing all of the rocket propellant needed for the trip back to Earth with us, the ISRU, which is essentially a small chemical processing plant, would take the readily accessible elements in the Martian atmosphere and convert into fuel for the return flight home. This method drastically decreases the overall mass and cost of the mission. The ISRU will require about 23 kilowatts of power, and all that power will be supplied by the 3 kilopower reactors, which can produce up to 30 kilowatts. Although the ISRU will require a large amount of power to produce the fuel, the propellant will be made and ready within that 20-month period before the manned mission leaves Earth. So only a small amount of power will be needed to keep it at the required temperature once the crew arrives. Most of the 30 kilowatts of power will then be redirected to the Mars base.
These kilopower reactors, individually referred to as Crusty, are nuclear fission generators that use uranium-235. Each Crusty weighs 1,500 kilograms, generates 10 kilowatts, and has a large radiator that folds up for transportation. The 3 Crusties will run during virtually any condition on Mars and are tolerant of dust, unlike solar arrays. It is our most reliable energy source and therefore will be in charge of producing the 22 kilowatts needed to produce all of the life support subsystems.
20 months after Crusty first lands on Mars, the Compact Telescoping Surface Array, CTSA, along with the rest of the mission base, touches down on the red soil of Mars. The CTSA lands on Mars in its stowed form, fitting inside a 10-meter lander. Its design has many variables that allow for any desired stow and deploy geometries and has been designed to withstand the Martian environment. Once in its secure location, the 6 solar array rings around the lander autonomously deploy. Fully extended, their length measures 22.5 meters, with all 6 wings providing a total solar area of 1,000 meters squared. The CTSA produces up to 72 kilowatts of energy during clear summer days and 45 on clear winter days, and will be responsible for providing the remaining power required by the base. During the day, the excess energy produced by CTSA will charge the 3 lithium batteries located within the HAB modules, so that the nighttime power needs of the base can still be met.
All of the stationary equipment's power needs will be completely met by the CTSA and kilopower reactors, but mobile equipment such as rovers need to be self-sustaining and require a lightweight, transportable energy source. The Ultraflex solar array is ideal for this application, as it is very compact and lightweight and folds up for transportation. Its design can easily be adjusted to meet specific power requirements of different kinds of mobile equipment and can produce about 7 to 12 kilowatts. For power storage, we'll be using 3 lithium batteries that will be placed underneath the floor of the HAB. As previously mentioned, these batteries will be charged by the excess power generated by the CTSA. The batteries utilize Xeon Power's lithium technology, which has an ultra-high energy density of 640 watt-hours per kilogram. Each battery weighs 271 kilograms with a volume of 1.5 meters cubed, and the collective energy storage of all 3 batteries is about 520 kilowatt hours. That is enough power to support all the life support systems for 24 hours, as well as some other subsystems, assuming Eclipse can slightly cut down on their power draw during an emergency. So in the case of a power emergency where there is a total loss of electricity, when the batteries are fully charged, it will give the mission crew 24 hours to fix the issue before their lives are in imminent danger. If the power cannot be brought back online, that is also enough time to plan an emergency evacuation to the ERV.
With 3 kilopowers, the CTSA, and 2 Ultraflex arrays, we will be able to produce a minimum of 89 kilowatts during the day with a maximum of 126 and a constant 30 kilowatts at night. These energy sources, along with the lithium batteries, will easily supplement the needed power of the base and allow for the mission to operate smoothly.
Overall, our total mass for this base will be 188,000 kilograms. Our total cost will be $8.6 billion, and it will require 8 launches to transport this mass to Mars. Using 2 launches per opportunity, which is roughly every 2 years, it will take 8 years to get this infrastructure on Mars with a budget of $1.1 billion per year. Now, I will hand it off to Kate to talk about how this internship impacted all of us.
Throughout our experience, we have all learned so much about mission design and our futures in STEM. Our mentors have been so helpful and supportive, and I speak for the team when I say that it was their guidance and enthusiasm that transformed an already great experience to a phenomenal one. So thank you.
That concludes our presentation, and thank you for your time. But before we finish, we'd like to thank both our mentors and the SEAS program and staff members for this amazing experience that we got a chance to participate in. Now we invite you to ask any questions that you might have.